Equilibrium.
Equilibrium is a state at which the rate of forward and reverse reactions are equal. At this state, concentrations remain constant and the reaction is always happening. However, this only applies in a closed system. These graphs show equilibrium. One charts the concentration of products and one charts the concentration of reactants. This graph shows the rate of reaction and shows them becoming equal as equilibrium is approached. There are two main types of reactions: endothermic reactions, which form bonds and which take in heat, and exothermic reactions, which give off heat. A potential energy diagram shows the amount of energy used throughout the course of a reaction, and we can draw these for both endothermic and exothermic reactions. On a potential energy diagram, the forward reaction or reaction progress is graphed along the x-axis, and where potential energy levels are graphed on the y-axis. The different parts of a potential energy diagram include the products, the reactants, and the activation energy.
Collision theory says that for a reaction to occur in the first place, molecules need to collide to react. And they need to collide with a certain amount of kinetic energy at a specific orientation. This makes for an effective collision. With effective collisions and the rate of reaction, the more effective collisions there are, the higher the rate of reaction, or faster. Some of the things that affect the number of effective collisions are temperature, pressure, concentration, and surface area.
Temperature or kinetic energy affects the rate that molecules move around, and higher kinetic energy means that molecules move around faster and are more likely to collide, producing effective collisions. Concentration is how much of something there is in a certain space. So higher concentration means that molecules are more likely to collide because there are more of them in an area. Most collisions, in turn, mean more effective collisions. Pressure pushes the molecules together, effectively increasing the concentration, which means more effective collisions. Increasing surface area allows for more collisions to occur than normal because the rate that collisions occur are faster due to more exposure. Surface area in a reaction can be increased by grinding up a reactant. Another way to speed up reactions is to add a catalyst. A catalyst will lower the activation energy required for any reaction, allowing it to progress faster by giving the reactants energy to form products.
KEQ is equilibrium constant, which is concentration of products over concentration of reactants. In a sample equation with products A and B and reactants C and D, you would do KEQ equals the concentration of C raised to the C times the concentration of D raised to the D over concentration of A raised to the A times concentration of B raised to the B. Equilibrium constants can serve as a measure of the extent a reaction proceeds to completion. When K is greater than 1, there are more products at equilibrium. When K is equal to 1, there are similar amounts of products and reactants, and when K is less than 1, there are more reactants at equilibrium.
Putting different stresses on systems at equilibrium has varying effects. However, the systems overall follow Le Chatelier's principle, which says that if you disturb a system at equilibrium, the system will try to undo what you have done to establish a new equilibrium. Some of the different stresses on equilibrium may include adding/removing a reactant or product, adding, removing heat, or increasing or decreasing pressure. Adding reactants means that there are more reactants to react, so therefore more products will be produced. This is called a shift towards the product side. Likewise, removing reactants does the opposite, and with less reactants to react, there will be less products produced, causing a shift to the reactant side. adding products means that more reactants are necessary, whereas removing products means less reactants are needed. Adding heat to an endothermic reaction means more products, as when heat is added, an equation will shift away from the side with heat, and in an endothermic reaction, heat is on the reactant side. Taking heat away results in less products as the equation shifts to the side with heat. Vice versa, for an exothermic reaction, adding heat will cause it to shift towards reactants, and taking away heat will cause it to shift towards products. Increasing pressure shifts the reaction to the side with less molecules, and decreasing shifts the reaction to the side with more molecules.